let's look at example 3 over here. Find the volume. Let's say each parallel cross section is square. Okay. So it's just a matter of reading the wording and try to understand the picture with them. So each parallel. Sorry for the writing a little cut off. So now here's how it looks. And allow me to draw that in this space perspective way right here. So we got the x-axis, okay, and then the y-axis is coming out this way. So kind of like we're looking at a floor, right? These are flat, 3D perspective view right here. Right? So the origin right there, 1, 2, 3, 4. And then we're looking at the base, right, is the region bounded by this curve here, right? And then the x-axis between 0 and 4. 0 and 0 and 4 is there in the curve. So you can set your own scale with that, right? That's kind of like that. So that's a nice square root function, right? But you sort of like we're treating that as a base right here, as a base region. Now that's our region between 0 and 4, the curve, the x-axis from 0 to 4. So each parallel cross-section, right? So of course all of the cross-sections are parallel to each other. But now we want to add in a little more extra description. Each parallel cross-section right here is perpendicular to the x-axis. Okay. So the way how we're drawing that is like this. So these are the parallel cross-sections. See what I mean? Okay. Parallel cross section. Look like that, where they come from the stripe, right? Those stripes are perpendicular with the x-axis, and then from those stripes we're erecting up the square, right? The square is coming up like that. Right? That's how it looks. Of course, forgive me if I'm not drawing it correctly enough. That's the idea of that. That. So that's why the idea now is that the squares, the cross sections here, those squares, they get big, they get small, depending on where we place our cross section, right? So where we place our cross section here was in respect on the x-axis, right? So depending on where we place it on the x-axis, right, we have a different square areas here in the cross sections. You guys follow with me on that still? Okay. All right. So from that way, with the fundamental I introduced, we need to identify the thickness. So in a way, how we place the picture, right? So unavoidable that you gotta be able to draw the picture a little bit, okay? Right? Understand it. Okay? So in the way how we place our squares like that, then what can be decided as the thickness? The dx, right? Yes. We got dx. Very good. And so now, once we got the thickness, the next thing is to calculate or to figure out a formula, right, or a general rule to determine the cross section area. Cross section area. So apparently, it was described here. I mean, right through the description, each cross section here is a square, right? So this side, whatever that is, has to equal to this side going up. So, and then depending on where we place our cross section, right, we're going to have either a small square or a big square. It's growing or it's shrinking, all depending on where we place our stripes, so that we produce a vertical cross section being a square. You have the idea right now. So think about it. So any of the stripes here, if you put it right here at x equal whatever, right, at some x right here, then the stripe got, the square here got one of the edge being what? Being the square root, right? And then the other edge has to be the same height. It's also the square root. You guys follow it? Right? So square has area famously known as what? One edge being square, right? You guys agree on that? Okay? So now we have come to a generalization right there. At any place inside, anywhere inside of this region, right, of this base region, anywhere on the x-axis, that we place a stripe, right? We place a stripe. So wherever x is, right? We got our square's area calculated as square root of x all squared. That's the way how we calculate it. So every problem has a different way, but we base right out from the description of our cross section. And so right from that point right here, once you've gotten that calculation of the cross section area, then once again the same fundamental here. Just let me remind that again. We need the cross section area, right? We multiply that with the thickness. That gives us the volume for volume of one section, right? One cross section. But then we're accumulating all of those cross section volumes from the start, right? To the end, setting up, and we got the total volume. That's how we're getting it. Now in this case right here, the cross section's area is the square root of x all squared. We multiply with the thickness, we get the cross section's volume, thin volume, right? And we're accumulating all of that from, so now from where to where? The picture was saying, it's right here. The starting point is, the first line is being placed right here on the x-axis, right? Which is, it's really shrinking our squares to something like 0 area, right? But then the square is going to keep getting bigger and bigger as we come toward ending at 4. So the accumulation is happening anywhere from 0 to 4. Now we got for ourselves a clear idea. All right. So in that way, accumulating from 0 to 4. That gets us the volume. All right. So now it's just a matter of once you've got the integral successfully set up and completed, right? We can go ahead and finish the work here. So it's the same as the integral from 0 to 4. The square root of x is going to be just x dx over there. Okay. Now that gives me 1/2 x squared according to the fundamental field calculus, right? 0 to 4. That gets me just simply 1/2 times 4 all squared, right? And then the other one here, which is it's going to be all 0 out. So 4 all squared is 16 divided by 2. We're looking at 8. Right. Good. All right. So at this point, we've been rolling into areas and volumes and all that, right? And throughout other places, what that I'm teaching the exact same material over here. Somebody mentioned this particular question that also it's good to share with any one of you guys are learning. But see, we've never been concerning about the units, right? When it comes to volume, sometimes it's go cubic feet to cubic meters, something like that, right? Or area is going to have to be what, square feet or square meters or square centimeters or whatever, right? And how come in calculus, see, we just disregard all of that. So the truth behind the scene is that's always been some units, but so that now, if we quickly roll back to that very beginning problem, let's say that function x squared that I promoted in the very beginning of our order, that's right? And then we did so much work, and at this point, there's no doubt that this x squared function, when you restrict that between 0 to 1 here, and we calculated the area, okay? The calculation you guys have seen many times, that area there, when we were doing the integral from 0 to 1, right, of x squared, right, that area come out being a 1/3. You guys follow it? Okay. Let's see 1/3. 1/3 of what? What's the? If now you're asking me at units. Think about it. When you're working in the world of algebra with graphing, units are depending on how you decide the units for your scale 1 right here. So on this graph here, that units from 0 to 1, it could be a 1 feet, 1 foot, it could be a 1 centimeter, it could be a 1 meter, whatever. And so all it says now is the area being a 1/3, it means it's a 1/3 of the whole square area. See what I'm saying? Huh? So if this is a 1 inch, then that means this is a 1/3 square inch. Because the square inch is right there. See what I'm saying? If this scale is from 0 to 1 is a 1 meter, if that being said is a 1 meter, then your area here is a 1/3 square meter. Does that make sense like that? And so in the same way right here, in our picture, if we're looking at 1 here, and a 1 up here, that cube right there, right, is being a, that cube being a, you call that the 1 foot, right, on each dimension right there, or from 0 to 1, right? Then your final answer here is in cubic feet. You want to say no, it's all relative to how we scale our line with that, our graph system, which a lot of times we never have to pay too much attention to. Okay, so that's the idea of that. All right, and then later on, when we actually push these into some real physical, some physics applications of those, right, which come in the next couple of days or so, right, then we're gonna have some real units as well. Okay, so let's look at another one. So how about here? I'm gonna call that simple 4. We find a volume. Right. Highlighting that down. Some problem like the earlier one, it has the equation, something like that, and a problem like that, it's a lot more general. Right? We just have to read the description and be able to, and then there are a couple of things that's actually under our control right here that we can decide. Okay, you guys ready? So let's just have a look, think about or have an imagination of this base area right there. The base is a circle, right, of radius 3. Okay, circle. Center information is not even given, but it's a circle, radius 3. So wherever the center is, that radius is 3. You guys all good? Okay. But now from that region, from that base being the region, just think about it. All it says is each parallel cross section. So which way does the cross section go? In this way, that's okay. Any way that your cross sections go, but once you make one direction right here, all cross sections have to be of the same being parallel. That's why it's always important of each parallel cross section. Right? So the rule here is that all of the cross sections, all of the slices, right, got to be always parallel with each other. Okay? And then so in this way right here, think about on these parallel cross sections, we built an equilateral triangle on top of that. See what I'm saying? Huh? Okay? So that's all the description says. So in that way, think about it. We actually have our control in a certain sense right here. Think about the x-axis, right? Think about the x-axis. We can purposely put that circle right, center right at the origin. So that means it goes -3 here, 3 here. And of course, I'm not an artist, so that's a circle.
That looks pretty good to me.
Is that right? Thank you.
It's surprisingly 3D.
Someday I'm doing that good. Someday I'm doing more good. Okay. Maybe the next day you're gonna have to be laughing at my picture. So that's a 3. That's a -3. But then, see, so like I said, we can purposely decide to put this circle center right at the origin, right? And now, right on top of that, we can also purposely decide, because like I said earlier, once you have the circle, what's the direction of your slices? Doesn't matter. All it needs here is that the slices are parallel to each other. Okay, and so on top of these slices, we build an equilateral triangle. See what I'm saying? So we can purposely, in that way, we can purposely build those stripes to be. Let's make the stripes perpendicular to the x-axis. Okay. So those slices are now perpendicular to the x-axis, and then of course they are parallel with each other. So now on top of that, now we build the equilateral triangle. Think about it. Equilateral triangle coming up like that, right? But right on the x-axis, that's where the height of the equilateral triangle. You guys see the picture right there? So the cross surface have to always stand straight up, right? Stand perpendicular to the regions. That's of course, it's needless to say at this point, it's one of the required. But now these cross sections being parallel, but we can decide which way they are parallel, right? And so we purposely put them in a way that they're perpendicular to the x-axis. And we're going to put that completely under our control again. Are we good? All right. So now, needless to keep asking you guys this question, isn't it obvious? That in the way we decide our picture, right? The thickness here is the dx. See that in the picture right there? And then let's figure out a way to come up with a cross-section area. Now, okay, cross-section area is a little challenge in this case right here. What area of a triangle is always 1/2 times base times height, right? See what I'm saying? Huh? But think about this right here. For your triangle, when you put the x-axis like this, right? Think about looking straight down like that, right? Think about the y-axis coming out this way, right? Then your 3 is here, -3 is here, right? Your circle goes. Actually, applying the y-axis is going this way, right? But your cross sections are going like this. You guys see what I'm saying? Huh? So the idea of an equilateral triangle, how many people remember it? So this is one edge of the triangle, okay? And it comes out like this. But see, all 3 edges have to be equal length. Remember that thing? Okay? And so that means we gotta be able, we can figure out how far this length is. That's our base, right? This length right here is our base. But we need to figure out how the height stands up. You guys follow it? Okay. So the base is clearly, and by the way, so now once we're looking right down at that the base region right here, then the length of the base here, it has to be the difference between the upper dome right here, the upper curve right here is the square root of 9 minus x squared. You guys follow it? It's a radius circle. I mean, it's a circle with radius 3, and we purposely put that at the origin, right? So it's square root of 9 minus x squared for the for the upside, and then it's here it's minus square root of 9 minus x squared for the low side. You going good? And so in that way, the base here has to be the difference between these two, right? So in that way, I'm seeing the base is going to be square root of 9 minus x squared, right? Plus the square root of 9 minus x squared, okay? Okay? Because minus the -1, right? Minus the -1 is a plus. So in the end, it turns out shockingly that the base is just 2 times, right? 2 times of this expression. Okay? So I'm going to erase this and write down the better version. So it's a 1/2. This is the actually, so sorry, it's a 2 times square root of 9 minus x squared. That's the base. We got base, and now we're waiting for the height. And of course, it's going to have to multiply with 1/2 in front, right? So let's figure out the height here. So for any triangle, this is one beautiful thing about the equilateral triangle right here. These edges are, let's say it's all S, S, and S, right? Those are all the side lines here. You guys still remember, and I mean, you should have done geometry in your high school, right? Any of your high school, right? Any of your place you've learned through. Remember the way to calculate the height of an equilateral triangle? Well, anytime it's equilateral triangle, then that height is also the median, because it's goes right through the midpoint of the edge here. So these two sides are equal. Remember that? Which is exactly 1/2. So if it's S here and the S there, then this little length right here is a 1/2 S. You guys remember that? Right? Now you can calculate how big this is, how long this is. All right. Pythagorean theorem. Quickly. Pythagorean theorem. S squared. So H right there, H squared has to be what? S squared minus 1/2 S all squared, right? Because according to Pythagorean theorem, H squared plus 1/2 S all squared has to equal S squared, the hypotenuse. You guys following? Okay. Maybe let me draw this H right here in red ink to make it easier to recognize it. Whoever missed that famous mathematician that came up with the Pythagorean theorem. Right? He was the one that unlocked a lot of mysteries for this earth right here. And so doing this work right here, it's going to turn out what this. It's going to be a 1/4 S squared here, right? So S squared minus 1/4 S squared, and I think I've left this here long enough. So let me clear this out. That gives me a really a 3/4 S squared, and you can use your algebra to double check to be on that, right? And so H itself means what? H itself has to be taking the square root of that, so it's going to be a square root of 3/2 times F. Okay, square root of that. See? So in our case, I'm talking about S being this length here, right? S being this length here, S squared. So I mean, so now I'm going to multiply. I'm going to multiply with a square root of 3/2 multiply with S. But S being the two times again, right? 2 times square root of 9 minus x squared. That's the formula to come up with our area of the equilateral triangle. Yes, it took some math, right? But look at all of that, the good usefulness comes out of it. This is base, and this is what's up here, height, right? Base times height times 1/2, right? All right, so now in that case, we're ready for formulating that area of the cross section, of that interval actually. And so with that setup, we've had right there that in the end, our cross section, each of the cross sections become a 1/2 times and why don't I just reduce that to a nicer form like that? So square root of 3 times the square root of 9 minus x squared all squared multiplied with thickness. We're accumulating from. Let's go back to the picture again. The accumulations of those slices, of those slice volumes, right, happening from -3, right? 3 again. Because -3 is the first slice on the left that we can put, right? And then +3 is the last one that we can put, okay? Those vertical slices. All right, so in that case, we're accumulating all of that from -3, 3. There we go. And that completes our interval setup. Then, of course, I canceled out all of the 2's, right? You guys can see that? And then the square here will eventually cancel out with the square roots, like this. And I can bring that square root of 3 in front, like this. So square root of 3 times the minus. In a row from negative 3 to 3, 9 minus x squared dx. So when it comes to this point right here, you take your own route to solve this, to calculate this interval on its own. But just the idea when it comes to these problems, my main aim is to show you how to set up the interval. Right? You do the calculation, but once you've got the interval set up, then you can take your own route. When I would do it personally, I just want to remind you that you see for this particular problem right here, I recognize, right, it's an even function. Okay? And so we get even. And we can purposely rewrite our interval as it's a 2 times square root of 3, and then I'm turning that interval into anywhere from 0 to 3 only. Okay? And then it's making it easier. I mean, less calculation effort at some point. So now it's going to be 2 square root of 3 multiplied with 9x minus 1/3 x cubed. Okay? We're evaluating from 0 to 3. Right? Now the 0, that's where we can do some work. Is the 0 part here is going to make it all 0. Right? We only need to substitute the x equals 3 into our antiderivative here. So 2 square root of 3 times 9 times 3 minus 1/3 times 3 all cubed. Okay. Right? And so it should come out 6 square root of 3. Right? You can double check my math. So that's another problem. That's how we can calculate the volume vector. Constructed by finding the volume of the thin slice. Some problem it already got it has a more set out of a base region. Some problem is a lot more open, and we can put it in the way we want, right? To make the problem solving a lot easier. And the next example I want to bring in right here, it's completely a 5. It's still a volume thing right here, but also want to show you guys a little bit of a proof. Let's call it example 5 here. Okay, leave me a space right here, and I can write it down completely. But how many people remember the formula to calculate the volume of a square pyramid? This is where Google is useful right there. How about Google? Ask you Google, Mr. Google, what's the volume for a square pyramid? Like those pyramids in Egypt. Okay, that's the picture. The base is a square, right? It goes to a pyramid. Okay, so I'm talking about something like this. Then something like that, right? That's called a square pyramid. So we got, of course, definitely we have to have a height, right? There's a height, and then these are S and S, definitely. Based on the base square thing. That's the square pyramid. So what's the volume of this? Something like that. What's the formula for the volume?
Should be the base x squared multiplied by height over 3.
Yeah. So the base being the square, so it's S squared, right? Multiply with height, you want to say, no? And multiply with what? 1/3, right? You said over 3. So that's the formula we've learned from Google, right? Let's use calculus, right? To prove that the volume of a square pyramid V equals 1/3 S squared times height. Okay, where there you go. Let's prove it. See, that's what mathematicians do. We don't just simply. When you were how long ago did they show you guys this? I mean, generally in terms of learning, right? We start learning about these things. If I remember correctly, like somewhere 4th grade or 5th grade, something like that. Okay? When you knowing how to multiply properly, right? I mean, they didn't say it as a square back then, of course. When you were 4th grade or 5th grade, they didn't express it in terms of the square, but they didn't say, hey, the volume there is h times h, right? And multiply with a height and multiply with a 1/3. You see what I'm saying now? Okay? And then when you grew a little more mature, right, in a formal high school geometry, then yes, we call it s squared times height, right, times 1/3. See what I'm saying now? But then now we want to prove this. Right? We want to prove this using calculus. Right? The plan is to use calculus. See what I'm saying now? All right. So here's how I'm seeing it. The picture may have some various height and all that, but all in the end, here's how I'm seeing it. On the x-axis, right? The y-axis here, space and respective thing, right? You can think about, you can slice your pyramid into halfway like that. So this is the base region where you're viewing an isosceles triangle. You guys are doing that together? Okay. And then so of course this length here is S here, S, oops. It's the whole length here. Right. That whole length being S. Okay. That's a base region, right? It's a base region. But then right from that base region, of course, and then this line from here is H. And then right from that base region, we actually set that in a way that it's right in the middle. Think about your square pyramid like that, right? I'm putting that so that the base region looks like right here. That picture is right in that cutting line in the center, in the middle. That's what I intended to do. See what I mean? That's here. Yeah. Right? And so right around this, right, there's a square so that at each slide, right, there's a square coming out. See what I mean? Right? And then depending on where we put our slides, when we put our slides here, right? So the slides are in the way how I put the picture purposely, right? And the slides are perpendicular to the x-axis. You know what I'm saying, huh? So we take full advantage on the x-axis, that's right. And so for those slices, see, anywhere of those slices, we build a square right out of that. See what I mean? That's why it's from big, it gets smaller, right? Advantage to one point again. So now let's figure it out. Let's figure it out. So, right from that picture, right? More space, that's why. Draw it like that. Right through. The base is right there. So, just think about it in a way how I'm drawing my picture like that. Then, what do you think the thickness is? Still, those stripes are parallel, I mean, perpendicular to the x-axis? Yeah? Yeah, I agree. So the thickness is dx again. Good. And now let's look right at the base. See, that red triangle right here I'm drawing in my actual pyramid is this version of the base, right? So, and now if you're looking right at right down on the top here right here, that base looks like that, right? And the slices go like this. You don't know? The slices go like this. That's why it makes sense to be a dx for the thickness, right? But now think about it. There's a square, but the square doesn't go completely up like that. The square goes halfway down, halfway up, right? You know what I'm saying? But in the end, we need to know, because no matter where we place the square, the two sides we do right here will also equal to that length there, right? You guys following? All right. So what's important here is just critically need to figure out how to determine that, the length of each of your stripes here, where you put that. Right? So anywhere you put that on the x-axis, right? How do we determine that? It's a line, isn't it? It's a line, right? Some information about the line that you know. It stops right here at h, right? Because that's the length, that's the height of your pyramid, right? This line right here, from the tip, we put the tip at 0. I should have also mentioned that. Right? We put the tip of the pyramid right at 0. And so the base is at h. Are we good with that then? Okay? And so in that way, and if this side right here is s, then that means it's a half s here. Do you guys agree? It's half s here. Now tell me, is there a way you could figure out the line here, that line, because this line is just a matter of, and the picture itself is pretty symmetric, right? Pretty symmetric. So all you do is figure out from how much that is from the x-axis up there, and we double that, right? It gets us the total complete length. Are we good? So what matters now is let's figure out a way to, and we come up with a function of x, right, for this line. It's a line. I just said it. It's a line. Slope, right?
I'm thinking right now, just spin it.
What's that? So what's the slope for this line?
1/2 s over x.
Yeah, 1/2 s, right, over 8. You guys agree?
Just spin it.
Yeah. And so it's gonna make it just simply a 1, or simply a s over 2h, right? That's the slope. The slope m again. And it goes right through the origin, right? So your line here is y equals s over 8. X here. It's dependent on x, right? Anywhere we put the stripe effect, right? So that's the curve. But then now, that's just the curve regulating the stripes. But now, as a matter of fact, for the cross sections, right? The cross section area, for each cross section area, what's the general regulation or generalization of each cross section area? It's going to be just simply, it's 2 times, right? It's 2 times of s over 2h times x right there, and then we square that. So this is going to be just the h, right? The length of the h on the base, right? Because the curve right here, you have to imagine the curve right here is just that curve. But the x right here, in terms of x, right, it's 2 times of that. 2 times of that. So eventually it will cancel out with that 2 as well. So that's why, well, maybe I should have noted that, right? So each x right here, each x right here, that will be 2 times s over 2h, right? Times the x, depending on where we put down that x-axis. All right. And so now squaring this, and cancel. So we got s squared over h squared times x squared, right? All right. So that's the area of the cross section. So for the integral to calculate the final volume. Okay, so cross section's area is a s squared over h squared times x squared. Right? And then we multiply with thickness dx. And all of these here we're accumulating from, so where do we start the accumulation? Where's the first line that we can accumulate? From 0. Because we put the tips right at the the origin. The tip right here, so the first line comes right here. And then depending on, as we go further out, right? Then those slices get bigger and bigger right there. But now, where do we end the slicing? Where do we end the accumulation? H. Yes, H is where we end accumulation. Right. There you go. So you got the volume completely set up as an integral. Right. So now when we're looking at this integral, there are variables all over, but in the end, only the x is the one that we're is the one that we're integrating, because that's in respect to the dx right here, right? So in other words, the s squared and the h squared are considered as a coefficient. So now advancing over to the next step, again, I'm looking at s squared over h squared, right? Integral accumulation from 0 to h on x squared dx. Okay. Okay. Now anti-derivative rule. I mean, fundamental theorem of calculus says we're looking at s squared over h squared times, it's a 1/3 x squared, and x cubed, right? And we're evaluating from 0 to h. Right? See how nice that is? It's not turned into, so the s squared over h squared still remains the same for now. Multiply with 1/3, 0, substituting in, making it all 0 out, and we have h cubed. Good? Now the h cubed we cancel with that h squared here. Right? That's leaving behind here. So now we have got our volume equals 1/3 times s squared times h. Ladies and gentlemen, we have proven it. The volume of a square pyramid. Okay. So the the Egyptians found that long ago, right? I mean, of course, calculus wasn't around at that time yet, so they didn't use this method to prove it. They used other methods. Okay. But for us here, when we come up with calculus, right, we can dig back all of those results and give it a completely inside-out development. Right? Completely new proof. Right? So for you guys already advancing up in math here, just think about the idea here. Where do those pyramids come from? Like a square base pyramid like this, right? I'm trying to point out a way to assist you on if you think about it, if you're comparing that, so square base here, right? If you compare that to an actual cylinder, square cylinder, I mean a square. This is not a cylinder. They call it a square prism, right? Yeah, so it's a square prism like that. But it's always, see, the pyramid version is always 1/3 of the prism version. See what I'm saying now? That's why even when you go to a cylinder, right? Whatever the cylinder is, pick a little point in here, that becomes a cone, right? That's always 1/3 of the cylinder version. Okay? See what I'm saying now? Okay. And so even when your prism here is a rectangular prism, right? Actually a triangular prism. See what I mean? Just like that, right? Then you pick your tip wherever that is, right? And you draw and that becomes a triangular pyramid, right? or a tetrahedron, but even more like a pyramid, a triangular pyramid. It's the base is a triangle. It's also a 1/3 of whatever that prism is. It's always a 1/3 ratio. And that's why these things is easy to remember. The height of your pyramid, the height of your prism, right? Which is also the height of the pyramid. You know what I'm saying, no? Right? That's why it's going to be S squared times height. That's for the prism, 1/3 of that. You get that? And then for cone version like this, see, we need area of circle. So area of the circle is pi, right, times r squared. And so times with the height, that gives you the cylinder. Okay. But now a 1/3 version, that gives you the cone. You get that? Right? That's the idea. And the Greek, whoever the ancient mathematicians, that's what they've proven. They've proven that through experience that, hey, they compare between the pyramid version and the prism version. They always recognize, hey, it's roughly a 1/3 ratio. They recognize that. That was their proof back then. But for us, now we use a precise calculus. All right.